Okay, so once again, good afternoon, everyone. We are going to start from chapter 1. Okay, give me a second to find the document first. Okay, so I hope everyone can see my screen right now. And all of you probably know that we are going to learn from this book, this PDF that you already probably seen from the group chat. So there are lots of chapter here, and we're going to start from chapter 1, which is about moles and equations. And I think you've probably learned this from your chemistry class with Buaras previously. And I'm just going to do a sort of kind of review. So this is how you read the book. I'm going to go to chapter 1. So here are the learning outcomes from learning moles and equations. We have to find use in terms of relative atomic mass, isotopic mass, and formula mass. Empirical formula and molecular formula, the more in terms of the Avogadro constant. So there are a lot of subtopic in this chapter, but we're going to discuss this slowly and thoroughly. And if I'm talking too fast or if you have any questions, just feel free to ask. So there are actually more. I'm not going to read this. Um, we're going to go through it on the way. So this is a brief introduction about chemistry. You can read this from here. So usually this book, at the very first page in the very first chapter, they're usually just theories. They're not really mathematics in it. So we're just going to start. So masses of atoms and molecules. So the relative atomic mass usually it is written with AR. So atoms of different elements have different masses. When we perform chemical calculations, we need to know how heavy one atom is compared to another. And an atom is really small that it is impossible to weigh it directly using the grams that we usually use. So that's why they come up with this. So scientists have chosen to use the isotope carbon-12 as a standard. This has been given a mass of exactly 12 units. The mass of other atoms is found by comparing their mass with the mass of carbon-12 atoms. And this is called the relative atomic mass. And you probably will see this symbol AR very often in chemistry. So this is the calculation. So AR element Y, average mass of one atom of element Y times 12, and then will be divided by the mass of one atom of carbon-12. This is an example of when you use the average mass of an atom. So that's pretty much about AR. And then next we have the relative isotomic mass. So isotopes are atoms that have the same number of protons but different number of neutrons. So we represent the nuclear number, the total number of neutrons plus protons in an atom. by a number written at the top left-hand corner of an atom symbol. So there are actually a few more of this kind of example, but different, some of them I think have um it's just same number of protons and then a different number of neutrons, and then they actually have vice versa that they have different names. So the thing that you should remember is for isotopic mass is that, I mean isotopes. They're atoms that have the same number of protons but different neutrons. So that's basically the thing that you really need to remember about isotopes. So is the term relative isotopic mass for the mass of a particular isotope of an element on a scale where an atom carbon-12 has a mass exactly 12 units. So that's about pretty much about isotopes that you will need to know for now. And then, so actually these all you kind of learn here in this chapter, they're actually high school level chemistry, A level chemistry, I think. There's the title on the book. So you don't really need to learn this truly for now. So basically just learn the gist of it. And now we are on to the relative molecular mass or MR. So this is basically the symbol that you will encounter when doing any kind of chemistry problems. So the relative molecular mass of a compound is the relative mass of one molecule of the compound on the scale where the carbon-12 isotope has a mass of exactly 12 units. So we find the relative molecular mass by adding up the relative atomic masses of all the atoms present in the molecule. So basically, this MR is combination of this AR. So AR technically is the mass a single a single atom. And now MR is actually the whole but I'm going to sort of zoom in so you can see the EVO clearly. So for example, here for methane right here, we have the formula CH4. And the atoms that are present for this compound is one carbon, and then we have four hydrogen. So we know that the AR carbon is 12, and since there are only one carbon in this formula right here, the compound, so we times that by 1, meaning that we have 12. And then for hydrogen, the AR of hydrogen would be 1. And since CH4, right here, you can see this compound has 4 hydrogens, so we times that by 4. So that would be 4 times 1. So 4 times 1 equals to 4. Then 12, and then we add that to 4. There, 12 plus 4, then we would have 16. So the MR of this compound would be 16. So do you have any questions so far? If you have any questions, just you can ask in the chat box, or you can just ask directly. Okay, so if none of you have any questions, then I'm going to move on to next subtopic here. So this is the relative formula mass is actually the same like the previous one. So we're going to see this again. This is calculated the same way as for relative molecular mass. It is also given the same symbol, Mr, for example, magnesium hydroxide. So this is the formula we can see right here. Okay, so I'm going to zoom this part. Okay, so now we can see this a lot more clearly. So right here, there OH is in the parenthesis with 2 outside of the parenthesis, as you can see right there. So one way to calculate this would be this way right here. You can see the ions present, the 2 plus right there. Okay, so okay, so based on the periodic table that I'm putting right now, so you can see that the mass of Mg right here or magnesium, it would be 24.3, as you can see right there. So there are no kind of any numbers around Mg right here, as you can see. There is only one. So when there's no any kind of number, that would be only one. So we times that 24.3 times one. So we still have 24.3. All right. So now we have OH right here with the hydroxide part. So now we need to find each of their masses right here. So the AR of oxygen, that would be 16. You can see that in the periodic table. And then the AR of hydrogen would be 1. You can see from the previous one. Right. So we can see the number 2 right there. So now we need to time each of the number in the parentheses by 2. So 2 times 16, that would be 32. And then 2 times 1, that would be 2. So we need to add this number up to sum up these number in the parentheses first. So we have 32 plus 2, that would be 34. And then after we get 34 right here, we add this up to 24.3. And that's how we get 58.3. Okay. Do any of you have any questions? Okay, so if none of you have any questions, then I'm going to okay, to small a little bit. So this is mass spectrometry, accurate relative atomic masses. So mass spectrometer can be used to measure the mass of each isotope represented in an element. So this is basically a tool. That's the tool, as you can see, mass spectrometer. So it's a very large and complex instrument where, well, as you can see right here, to measure the mass of each isotope. And basically, this is the compartment of it and how to use it. Actually, I've actually never seen one in my high school chemistry textbook, but it's really good to know this one. So basically, you just need to know what's the usage of that. So I'm not going to delve deeper into that. So this is the continuation of it. You can read it, this ebook from the group chat. So this basically how this thing works. You can see it right here in the kind of pink box right here. So now we're going to the next part right here. So the determination of AR from mass spectra. So we can use the data obtained from mass spectrometer to calculate the relative atomic mass of element very accurately. So to calculate the AR, can you say AR32 for short? We follow this method. So there are 3 ways. Yeah. So the first one, we multiply each isotopic mass by its percentage abundance, add the figures together, and then divide it by 100. So this is the formula, actually. So we can use this method to calculate the relative atomic mass of neon from its mass spectrum. As you can show in figure 1.5, the mass spectrum of neon has 3 peaks. So I'm not sure really how to see this again. Okay, what am I doing here? So usually there are actually kind of different kind of neons, as you can see, 20, 21, 22. So this is they're all isotopic right here. They have different abundance as well. I mean percentage. As you can see right there. So for the first neon right there, we have 90%, 90.9%. And then this is 0.3% only. And then this is 8.8%. So how, okay, that's too much. Okay, so now we need to time this number with the percentage. So 20 times 90.9, and then 21 times 0.3. And then the next one, we have 22 times 8.8. So after we get all these numbers, and we time these numbers, and then we add them up, add all of them. There's three, and then we then add all of them. And then we can divide it by 100, and then, well, we get this number, 20.2, which is the ER of neon. So that's basically this whole thing works. And if you have any question, you can just feel free to ask. So take note that this answer is given to three significant figures, which is consistent with the data given. So this is the data right here. You can see this. So that will be the mass spectrum of neon. So high-resolution mass spectrometer can give very accurate relative isotopic masses. For example, 16 oxygen right here. Oxygen, this would be the proton, which is 15.995. And then we have here, I think that would be sulfur. As there's, I need to find it for the tables. Okay, where were we? Okay, so this is silver with proton 32, and then the mass would be 32 point. Okay, so sorry about that. 21.972. It's kind of different from the book that I have right here, but it's about the same. So because of this, chemists can distinguish between molecules such as SO2 and S2, which appear to have the same relative molecular mass. So this is a question, we can skip that for now. Okay, so onto the next subtopic. This is basically all the things that you already needed to know about the basics of moles and their equations. So I'm going to like really delve deeper into any kind of topic. Okay, so the mole Avogadro constant. The formula of a compound shows us the number of atoms of each element present in one formula unit or one molecule of the compound. And while we know that two atoms of hydrogen has an AR of 1, combined with the one atom of oxygen, which has an AR of 16. Once again, you can actually see the AR or the mass of each atom. Usually they are located at the bottom of, I mean, yeah, you can see that in the periodic table. Usually below the names of each atoms, there will be the mass of them. So you can see that right there. Okay, so the ratio of mass of hydrogen atoms to oxygen atoms in one molecule is 2:16, no matter how many molecules of water we have. And this ratio will always be the same. But the mass of even 1,000 atoms is far too small to be weighted. We have to scale up much more than this to get the amount of substance that's easy to weigh. So the relative atomic mass or relative molecular mass of a substance in grams is called mole of the substance. So a mole of sodium, which has an AR of 23, weighs 23 G right here. The abbreviation for mole is mole. We define the mole in terms of the standard carbon-12 isotopes. So all of you probably know that usually the standard kind of measurement, we have grams or something like that. And in chemistry, when we are trying to weigh the atomic mass of an atom, then we use this grams called mole. So this is basically their standard unit when weighing an atom. So one mole of substance is the amount of the substance that has the same number of specific particles, atoms, molecules, or ions, as there are atoms in the exactly 12 grams of the carbon-12 isotopes. So this is kind of confusing, so just focus that basically this whole thing means that um a compound they tend to have this they always have the same ratio no matter um how many mass it has or 1,000 atoms or something. If the ratio is this, then it will always be the same. So it's pretty much constant. And then the measurement of atoms, you can call that mole of substance. So this is basically the summary of the whole thing. So you often refer to the mass of mole of substance as molar mass. So the abbreviation is M. So you have probably also encountered this a lot when doing any kind of chemistry problems right there. So M, capital M. Because if you use a small m, then that will be a totally different meaning. So molar mass is capital M. And this is the unit. It's usually placed in any kind of number. So G mod power of -1. So that's the unit of molar mass. And the number of atom in the mole of atom is very large. So 6.02 times 10 to the power of 23 atoms. And this number is called the Avogadro constant or Avogadro number. So this is actually standard, meaning that I think back in high school when we learned about this, usually when we were counting something, then we kind of multiplied with this to this number, any kind of number, and then because this is well, it's pretty much standard already, so we always use this number. And the symbol for the Avogadro constant is L. The symbol Na right here may also be used. So there are two symbols, capital L and then capital N, and then we have a tiny capital A right there. But I think this one right here is more commonly used than this one. I'm actually not really familiar with this one back in high school. So use capital L instead. So the Avogadro constant applies to atoms, molecules, ions, and electrons. So in 1 mole of sodium, there are 6.02 times 10 to the power of 23 sodium atoms. And in 1 mole of sodium chloride, there are 6.02 times 10 to the power of 23 sodium ions. And okay, I'm not saying this too much. So you can see it right here, 6.02 times 10 to the power of 23 chloride ions. So basically, the Avogadro number is something standard that, well, any kind of atoms, if 1 mole of sodium, 1 mole of sodium chloride, or any kind of 1 mole of something, that would be the same. So that would be this number right there, because it's the Avogadro constant. So it's pretty standardized right here. So it is important to make clear what type of particles we're referring to. If we just state moles of chlorine, it is not clear whether we are thinking about chlorine atoms or chlorine molecules. A mole of chlorine molecules Cl2 contains 6.02 times 10 to the power 23 chlorine molecules, but twice as many chlorine atoms, as there are two chlorine atoms in every chlorine molecule. Right, so if there are two, then that would be twice of this, so that's basically it. Sounds confusing there, but that is what it means. So this is a short history about Amade Amedeo Avogadro. I'm the founder of this Italian scientist who found about the Avogadro constant. To this short brief history about him right there. And then we are on to molar and mass. So System International base unit for mass is the kilogram. But this is a rather large mass to use for general laboratory work in chemistry. So that's why they have their own unit. So we don't use the international system base unit for chemistry only. Especially when trying to weight atoms or mole, that would be impossible. So chemists prefer to use the relative molecule mass or formula mass in grams. So 1,000 grams is equal 1 kilogram. You can find the number of moles of a substance by using the masses of substance and the relative atomic mass, AR or MR right here. So basically, when we're doing kind of chemistry works involving moles and something, these two, AR and MR, they would probably involve almost in everything. So this is the formula. So first of all, we have the number of moles, which is small. That would be the abbreviation. You can see it right here. This is the shorten. So sometimes they don't say number of moles. Again, we just say mole. So equals to the mass of substance in grams. So yes, we can measure the substance in grams, but not the mole right there. So you can see this is we still use grams. And when we have the molar mass, I think previously we have that already, the capital M right there. So G mole to the power of -1. So these two right here, grams and emo right here, they're actually the units. So here are actually some work example using the formula we have right here. So I'm going to explain it as we go through. So this is still pretty simple. So I hope all of you can follow, and if any of you have any questions or any confusion, just feel free to ask. So question number one, how many moles of sodium chloride are present in 117 grams of sodium chloride? So NaCl. So the AR values are Na, which is equal to 23, and then we have chloride, and this is sodium. And we have chloride right here to the 5.5. Once again, you can find the AR values on the periodic table. And then, but there are actually some kind of elements that you probably encounter a lot, so you probably memorize that. For example, hydrogen is equals to 1. You probably encountered that a lot, so it's probably memorizable on that part. So we have the molar mass of these two. So we add them up, 23 plus 35.5. Since NaCl, each of them has only one, what do you call, one mole of that. So we don't need to time them unless one of them has number 2, for example, right here, Cl2. Then we need to times this 35.5 with 2 before adding them up. But since this compound only have one of each, then we can just add them up without any kind of multiplication. So that would be 58.5 gram mole the power of -1. So you cannot forget about this unit. And now we are trying to find the number of moles. So we can see the formula before right here. So number of moles would be mass of substance divided by the molar mass. So we have the mass, which is written in the questions, in the problem, which is 117. So we put the 117 on the mass part. And then we have the molar mass, would be 58.5, which is what we got here. So we divided 170 by 58.5. So that would be 2. Don't forget the mole right here. Mole is basically the unit of number of moles. So there we have it, 2 mole. So that's how we do this kind of questions. Now we have the other question. But this is the other way around. We are not looking for the number of moles because it's already stated. So now we are looking for the mass. So what mass of sodium hydroxide, so sodium hydroxide will be NaOH, is present in 0.25 mole of sodium hydroxide. So first we need to define the AR values. So we have hydrogen as 1, and then we have the sodium that would be 23, and then we have the oxygen would be 60. So since all of them right here, they're only 1 mole, so we don't need to do a multiplication. We can just add all of them up. So 23 plus 16 plus 1, there we would get 40. So we already know that the molar mass is 40. And we also know that the number of moles will be 0.25. So now we can look for the mass right here. And the mass, since it is, so the way that we have to think about it, that we know that the mass is the largest of all of them, of the number of moles of the molar mass. So we need to multiply everything to get the mass. So number of moles, 0.25, and then molar mass, 40 times, so 0.25 times 40, we have 10 grams of sodium hydroxide. So I hope all of you can understand what I'm explaining. And once again, you can ask me if you want me to re-explain things if there any confusion. So this is the question. I think we can actually discuss that in our next meeting because I didn't really have the any app to write. I think I can I write here? I'm not sure. I think I can actually though. So calculate the mass of the following. So I think we can try right here. So we're going to do the first equation first. Since we've actually done a lot of this. So now we're trying to find the mass right here. So we're trying to find the mass right here. I hope you can write my handwriting. Okay, I don't think I need to draw this though. Can I actually? I think I can type this. So we're trying to find the mass right here. So we know that the mass would be the multiplication of MR here, the molar mass, and number of mole. So we know that the number of mole right here is already stated that would be 0.20. And now we have to time that. We have to time that by the M of this CO2. So we have C. So C is only 1 here, so we can put that 12, and then we have plus, and then we have to do this in parentheses. So O2 means that there are 2 oxygen atoms in this compound right here. So 2 oxygen atoms right here. So 1 oxygen, that will be 16. So 16 times 2 right there. So we have, so this equals to 12 plus 3, 2. That equals This equals to 44. So in order to find the mass right here, we input 44 right here. So 0 0.20, so I'm going to type this in my calculator. 0 0.20 times 44. There we have the results. It's 8.8 grams right here. Let's write this. So this is the result, 8.8 grams of carbon dioxide. Okay, so I hope you can understand this part. I'm going to erase this before moving on. Okay, I don't think I need to erase that. Okay, so there's actually another question right here. I mean, of substance in moles in each of the following. So we've actually done many of those already.
I have a question.
Okay, so what do you want to ask, Mark?
Look at the picture again, the figure 1.8.
1.8 right here. This.
Yeah, I was wondering what will happen if I mix it.
Okay, so from left to right, 1 mole of each of copper, bromine, carbon, mercury, and lead. Okay, so I don't think I'm not really sure about what will happen if you mix all of that, but this picture actually just kind of represents on the common of this, I think. What do you call this?
Does
Mole of,
does mixing it all up make a new things? I mean new elements?
actually I'm not really sure, but all I know that carbon and mercury. I think mercury is actually a pretty hazardous kind of element, while copper, bromine, and lead, I'm not really sure because it is actually a kind of metal. So I don't really think that you could get something out of it. Probably something, one element will destroy the other. I think that's about it. It's not really explosive something. No, I don't think that will happen.
Oh, what about is there a way to melt copper?
I think there is. You can actually melt that. It's pretty easy thing to melt because it's kind of metal. So any kind of metal it can melt. Yes.
So I was wondering, melt the copper, then mix it with something else.
Actually it depends on what you're trying to mix. If you mix copper with another kind of an other metal, then it would be an alloy. So it actually depends what you're trying to mix with copper.
There's water, right? Is that the in the glass is water?
I'm not sure it's actually water though.
Oh,
So
so,
from what yes.
so I was wondering, I put the melting copper at the water, and I want to see what will all the water turn to. The copper brown?
I'm not really sure what will happen if you mix a melted copper in water. I'm not really sure what will happen, but I don't think it will do really do anything. It doesn't really mix well, and basically it's well nothing, I guess. No really much any reaction that you will get out of that. Okay, so since water is not really any kind of explosive substances. And when you mix that with a melted metal, like copper or something, I don't think it will do any much reaction to it. Unless it is something that's really explosive, then yes, it will react to water as well. But copper, it's not an explosive kind of substance, so it will not do any kind of reaction if it is mixed with water. So I hope that answers your question. And if you have any questions, yes, you can ask again. Okay, so if it doesn't satisfy you well, then I can answer it again. You can ask any other question about that. Okay, so if you have no questions, I'm going to move on to the formula. So to find the mass of a substance present in the given number of moles, you need to rearrange the equation. So number of moles of substance right here. I think I've actually discussed this already. And then for the mass of substance, we can do that by multiplying the number of moles plus times smaller mass, which we already discussed in the example questions, right? Like this one. So we also have the mole calculations right here. So reacting masses, when reacting chemicals together, we may need to know what mass of each reactant to use so that they react exactly and there is no waste. To calculate this, we need to know the chemical equation. They show us the ratio of moles of the reactants and products. So the stoichiometry of the equation. The balance equations show this stoichiometry, for example, this reaction. So this is basically how you write the reaction right here. So 1 mole of iron is 3 oxide react with 3 moles of carbon. One oxide form 2 moles of iron and 3 moles of carbon dioxide. So this is basically the reaction that the outcomes. So the stoichiometry of the equation is 1, 3, 2, 3. The large numbers of that are included in the equation C, 2, and 3 are called stoichiometric number. So I think stoichiometry is actually pretty difficult. I'm not really good at it, to be honest, back in high school. But basically, this is the basics of it. In order to find the mass of product formed in chemical reactions we use, the mass of the reactants, the molar mass of reactants, and the balance equation. Oh yeah, I almost forgot to mention that. Yes, when writing this kind of reaction, we need to make sure that it's balanced, meaning that left and right, they are balanced. So I'm going to explain this later on if you have any questions. So this is basically what happens when iron reacting with sulfur to produce iron sulfide. This is the picture. Okay, so before this one, I'm just going to, okay, so material reaction. So we have a work example just to clear up the previous part right here. So at number 3 right here, magnesium burns in oxygen to form magnesium oxide. This is right here. Okay, so right here we can see that this equation is pretty much balanced. Okay, I'm sorry for that. So right here on the left, we can see that there are 2 magnesiums and then 2 oxygens right here. And then as the result, we have 2 magnesium oxide. We have 2 magnesium right here. And this 2 right here also means that we have 2 oxygen. Hence, this equation is balanced. So we can calculate the mass of oxygen needed to react with 1 mole of magnesium. We can calculate the mass of magnesium oxide form. So step 1, write the balance equation. As we can tell that it's already balanced. So multiply each formula mass in gram by the relevant stoichiometric number in the equation. So magnesium has a total of ER of 24.3. And then since we have 2 right here, we times it by 2. So we have 2 multiply times 24.3 grams. So we get 48.6. And then O2 right here, meaning that 16. It's automatically, since right here we have 2. So 16 is actually the ER of oxygen. And since it has 2, it is automatically multiplied by 2. So that's how we get 32. And then as a result right here, we have 24.3 for the magnesium, and then for oxygen, we have 16. So we need to add this up first before multiplying it by 2. So that's how we get 80.6. So 80.6 right here is actually the result of these sum of 48.6 and 32. So that's how we get 80.6. So from this calculation, we can conclude that 32 grams of oxygen are needed to react exactly with 48.6 gram of magnesium. So 80.6 gram of magnesium oxides are formed. And if we burn 12.15 gram of magnesium, which is 0.5 mol, we get 20.15 gram of magnesium oxide. This is because the stoichiometry of the reaction shows us that for every mole of magnesium burned, we get the same number of moles of magnesium oxide. So in this type of calculations, we not always need to know the molar mass of each of the reactants. So this one, we don't really know the MR, we only need the AR. We only need to know the mass in grams, and molar mass reaction is not excess. So this is another example. I think I'm going to finish this first. Okay, so we know that this equation right here is balanced because we have Fa2 right here, which is for iron. So we have this Fa2 right here, and then for the right side, we have 2 Fe. So both of right, left and right side, they have 2 atoms of Fe or iron. So this is balance. For iron, it's balance. So for oxygen right here, we have 3 right here. We have 3 oxygen atoms, and then 3 CO right here. We have 3 oxygen atoms again. So right here, we have O right here. So O 2 times 3. So when it's like this, we do multiplication. 3 times 2, that would be 6. And this 3 plus 3 would be 6. So we know that oxygen is balanced. And now for carbon, we have 3C right here, 3 carbons, the 3CO right here. So we have 3 carbons, and then we have 3 carbons as well. Hence, it is balanced. So now we already know that the equation is balanced. So calculate the maximum mass iron produced when 798 gram of iron oxide is reduced by excess carbon monoxide. So these are the AR values that we need to know. So now we do multiplication. So we know that right here, Fe 2 times 55.8 plus CO right here, 3 times 16. So now we get this result. And then we have 2 moles of iron. So you're probably wondering why this is kind of reducted right here. Yes, it's used by excess carbon, so we don't really use this anymore. We don't use the carbon, we can just ignore that. So here it is. 2 times 55.8. So we got 116.6 gram of Fe. So yeah, we can ignore these right here. So Fe2O3, so 798 grams. So we have here the result, just 2 moles of iron, 118.6. Then we need to divide it by 159.6, and then times 798 from here. And now we have 558 gram of iron. So you can see that in step 3, we have simply used ratios to calculate the amount of iron produced from 798 gram of iron of 3 oxide. Okay, I'm sorry about that. So basically, this is the work example of today's class. There are actually a lot more that I'm going to discuss in our next meeting, but so far, I think this is all for today. And I'm going to stop sharing my screen for a while. Okay, so that's all for today's class. And I hope you can understand. And if you have any questions, you can ask about the class before I end the class. Okay, so I think Sir Harry is here, and if um okay, sir, if you're here, if you want to talk, then before I end the class, I think yeah, you can say something first.
Well done, Michelle. Thank you so much. Welcome back.
Yes, thank you, sir.
Okay, welcome back. Okay, guys, Noel, Felicia, Tristan, always open cam. Now, maybe you can kind of, in 2 minutes, tell the class what is your first experience at IPB.
Okay, so about my experience in IPB University, or probably in Indonesia, you can call it IPB University. Um, Maybe it sounds more familiar. Well, this is my second week in IPB, basically. Well, I can say that it's pretty busy. It's a really busy week. I haven't really organized my schedule, and that's why I can only teach you guys in the second week. In the first week, I'm actually still adapting with the schedule. There are lots of projects, and this is only my second week there, but there are lots of project already, like group projects and other kind of assignments.
Yeah. How big is your class, chemistry class?
To be honest, I don't really have chemistry class, sir. I will probably take the real thing about chemistry, I mean biochemistry, in the
Mhm.
third semester. And for now, actually, it's pretty I don't really do any kind of study around biochemistry. I mean, at the university, I actually have physics,
Mhm.
sort of like about I think PPKN. It's
Ah,
basically like when you're in high school. When I was in high school, the subjects,
okay,
yeah, high school level.
okay, okay. This is good. So, guys, okay, Kat Michelle, please tell, do you think the program that you attended from TIS helped a lot on your first year, first semester?
So I think from TAS that I have learned, basically when I was in TAS, there are lots of learning that uses cognitive kind of thinking, and that's actually really helped me get admitted there because
Mm-hmm.
I was um I got admitted there by test, or you can call it
Mm-hmm.
Saksi Mandiri. So it's using tests, online tests. I think it's really, I mean, it really helped me from my cognitive learning ability from there. And there's actually a little bit of chemistry, a little bit of biology, there was on the test. So I think it's pretty helpful that I've joined TIS since I was in middle school. I think when I was 15 years old.
Yeah, this is great. Do you have any English class on the first semester?
Um,
English?
well, that's actually kind of the problem, sir. Some of my friends, I mean, from my group of friends when I got there, they have English, but I don't really have English, sir. I think I will get English in the second semester, but not in the first semester.
Oh, okay. So the other kid have to take the first semester English?
I think yes, actually, but I think it's actually kind of we switch places. If they got English the first semester, then they won't get it in the second. While if I don't get it in the first semester, then I will get it in the second semester.
Ah, okay. Okay, guys. Okay, remember this, what Kak Michelle just said. This is real. All right. To be admitted into one of these good school, PTN, they call it, right? Sekolah
Yes.
Negeri. Okay? So you really have to work hard as well. Okay? So Kak Michelle already show you the way how to do it. Okay? Work hard. It is nothing can be easy, but toward the end, okay, everything will be great. All right. Thank you again, Kak Michelle, to share your time. I know that you have been very busy, and hopefully that we, okay, TIS can always serve the student. Okay. All
Yes.
right. Thank you much. Thank you much, Kak Michelle. Okay. So now